The overall aim is to explain visual attention in neural terms, and in particular how attention can be controlled in a chaotically oscillating neural system. The networks to be presented are built from a few simple components that are all biologically plausible. The model neurons, the units, accept analog inputs and generate analog outputs representing firing rates. An excitatory input raises a unit's activation. An inhibitory input lowers it. The unit's output is the positive part of the activation. Importantly, activations vary over time with first-order dynamics. Units are arranged in rectangular layers, each unit being connected topographically to units in the same or other layers. There are two basic connection parameters: the spread of connections with Gaussian weight profile and the maximum synaptic weight. Shown here is a two-level network that exhibits a number of lifelike properties and is the basis for what follows. The principal units of both levels, shown in green, are subject to inhibitory connections, shown in red, both laterally and locally from a sub-layer of inhibitory units. Level 1 drives Level 2 excitatorily. Level 2 feeds back positively to Level 1 by disinhibiting the local inhibitories. So this connection cannot drive Level 1 directly, but can raise its gain. Visual stimuli topographically excites Level 1 principal units. When several identical stimuli are presented, one of them is attended, being represented by units that respond to changes from a probe stimulus. The other unattended loci are unresponsive. The two-level architecture can be used to perform visual feature integration. A set of Level 1 layers topographically represent features in the field of view, here color and orientation. These feature layers all connect topographically with the coordinator layer of Level 2, which acts to bind features based on a common location. Left to itself, the activity in a network, with appropriate connection parameters, will settle to representing one of the several stimuli. Here, for example, a green vertical bar. All stimuli are potential attractors for attention. The network can search for stimuli with specified features if the irrelevant feature layers are inhibited, and the attractor structure then becomes focused. This shows a two-level network reduced to its essentials. Visual input topographically drives a coordinator layer subjected to lateral feedback inhibition. This layer topographically drives the bump generator layer, which, via delay, provides local feedback inhibition to the coordinator. The presentation of input stimuli causes the network to oscillate in a way that depends on the number of stimuli. 2, 3, and 4 stimuli are represented by bursts of activity that cycle through the topographically corresponding positions in the layers. 5 and more stimuli are represented in a non-cyclical or itinerant fashion. While the itinerant mode of representation would be useful for exploring a complex visual scene, it would fail to keep track of a select few objects in the presence of many distractors. During a multiple object tracking task, we are capable of following up to about 4 objects simultaneously. Giving the coordinator layer a second feedback pathway that is positive and considerably more delayed allows 1 to 4 objects to be represented exclusively. 5 or more objects are ignored. Extra objects are excluded because their representations face high background inhibition and cannot be squeezed into the fixed period. Here, the network performs multiple object tracking. It is first shown 4 disks to track. The attention locus cycles around the 4 targets in a fixed order. 4 more stimuli are then added, and all are set into random motion. The layer activities and the position of the maximum is shown by the small red square. The oscillations generated by the network may have some bearing on brain rhythms. In animal and human studies, stimulus features that are modulated by attention appear to be carried by a low-frequency theta rhythm, whereas alpha is associated with the suppression of irrelevant information. In the model network, each object is represented by its locus in the coordinator map by a low frequency that can be equivalent to theta. If 4 objects are being tracked, the overall frequency is 4 times theta, and this frequency, which is prominent in the activity of the model's inhibitory interneurons, may be equivalent to alpha. The oscillations evoked by stimuli are chaotic. This is shown by their sensitivity to initial conditions in the state space plots during the representation of 3 objects. When the objects are identical, stationary, and turned on in sequence, the trajectory is a stable limit cycle. When the objects are presented simultaneously, the cycling is messier, and when moved around, messier still. The challenge, then, is to develop networks that retain information about attended objects in the face of chaos, and to make attention adjustable. For example, tracking 4 objects requires different network parameters than 3 objects. It is hypothesized, with some neurobiological justification, that attentional control is exerted upon the interneurons. A genetic algorithm was used to adjust biases on 3 classes of interneuron during tracking of 1 to 5 targets. High fitness was awarded to coordinator responses that closely tracked the targets with equal dwell on each. After testing about 200 networks, some good parameter combinations were found. However, even the best failed sometimes. More tweaking of both network parameters and architecture is required to subdue chaotic effects. Finally, this shows a possible mapping of the 2-level network onto neocortical circuitry. Cortex has an overabundance of neural mechanisms to implement the simple model derived here. Hopefully, the model provides a parsimonious interpretation of cortical architecture and function.